Imagine you wrote like just 240 lines of code and it
Yeah.
totally replaced 7 massive industry standard software libraries.
Oh, wow.
Yeah, and you cut your build time in half, your code runs up to 5 times faster, and you didn't lose a single decimal point of mathematical accuracy.
I mean, honestly, it sounds like a developer's pipe dream, right? We are so deeply conditioned to believe that building software means just stacking massive abstractions on top of one another.
Yeah.
We're taught that you never ever reinvent the wheel.
But today, we are looking at a masterclass in deleting code. Welcome to this deep dive where we are challenging that whole, just use a library for everything mindset.
Really refreshing topic.
It really is. So whether you are a coder who's currently drowning in software bloat, or you're just someone who appreciates really elegant, minimalist problem solving, you are going to love this. We are exploring a super fascinating case study from 2026 by developer at Look036.
Yeah, the project is called Slimming C plus FIR filters, replacing extensor with R.
Exactly, and it's such a powerful narrative.
It really is. Because it's fundamentally about what happens when you stop blindly trusting conventional wisdom, and you start looking really intensely at the specific physical constraints of the problem right in front of you.
Okay, let's unpack this monster they were fighting because to understand the triumph of this 240-line solution, we need to know what they started with.
Right, the bloat.
Yeah, the bloat. So the project is about designing C++ FIR filters. And for those of you who aren't in the weeds of digital signal processing, FIR stands for finite impulse response.
Which are basically mathematical filters used to clean up or modify signals.
Right, like equalizers in audio software or cleaning up sensor data. And the original setup for designing these filters relied on a library called Extensor.
And to be fair, extensor is an incredibly powerful, highly respected n-dimensional array library.
Oh, totally.
It is designed to crunch complex numbers across massive data sets,
Yep.
but using it comes with a heavy tax.
A huge tap.
Yet choosing extensor meant the developer had to drag in a staggering 7 external dependencies. I mean, we're talking about pulling in libraries like XTL, extensor blah, extensor FFTW, BLA, LabPack, and FFTW.
It's just wild. 7 massive libraries just to do some math. But here is the crucial insight, the real aha moment that kicked off this whole audit.
Right.
The FIR filter coefficients, which is just the actual data this massive stack of libraries was processing, they only have about 32 to 128 taps. Elements, essentially.
That's just tiny.
Right. So we are talking about processing data arrays that have maybe 32 items in them.
But that completely changes the rules of the physics involved here. You see, a library like extensor brings in heavy artillery, right? Like BMS acceleration.
Which stands for basic linear algebra subprograms, right?
Exactly. And it is phenomenal for massive matrices, like the kind you use in machine learning, because it is specifically designed to optimize for cache misses in your computer's memory.
Okay, hold on. For listeners who might be a bit rusty on computer architecture, why do we actually care about cache misses? Like, what does BLA actually do in that scenario?
Oh, sure. So think of your CPU cache like the top of your physical desk.
Okay.
And your computer's main memory, the RAM, is like a massive filing cabinet down the hall.
Got it.
A cache miss happens when the CPU reaches for a piece of data on the desk, realizes it isn't there, and has to pause everything to literally walk down the hall to the filing cabinet.
Which takes forever in computer time.
Right, exactly. So BLAs is incredibly smart about grabbing giant chunks of data from the filing cabinet and organizing them on your desk so you minimize those long walks.
But if our array only has 32 elements...
The entire array fits perfectly on the desk.
Wow.
Yeah, it fits inside the CPU's level 1 cache with room to spare. There are literally no long walks to the filing cabinet to optimize.
So bringing in a massive library like BLA to handle a 32-element array is, well, it provides absolutely zero benefit.
None. It is trying to solve a problem that doesn't even exist at that scale.
This reminds me of an analogy. Using a 7-library stack like extensor and BLA to process a 32-element array is like renting a massive commercial crane just to mount a flat screen television in your living room.
That captures the mismatch perfectly.
I mean, think about the logistics of getting the permit for the crane, blocking off the street, setting up the rigging. It takes infinitely longer than just picking up the television and hanging it on the wall yourself.
Exactly. The tool is just completely disproportionate to the scale of the job. And it gets worse, honestly.
How so?
Because the commercial crane of extensor actively slows you down in other hidden ways too, like lazy evaluation.
Okay, what is lazy evaluation doing here?
Well, lazy evaluation is a programming technique where the computer defers doing a calculation until the exact moment the result is actually needed.
Okay, makes sense.
Imagine writing down a very complex, highly optimized grocery list to plan the perfect route through a massive supermarket. If you're buying 100 items, that list saves you an hour of walking. That's what lazy evaluation does for giant data sets. It saves memory and redundant calculations.
But what if you were only going into the store to buy a single apple?
Then writing the complex list takes longer than just walking in and grabbing the apple.
Oh, man.
Yeah, for a 32-element array, lazy evaluation just adds useless computational overhead without any measurable gain. And then you have to factor in the compile times.
Right, the compile times.
These large libraries rely really heavily on something called template metaprogramming.
I know this is a huge pain point for C++ developers. Can you break down why that slows things down so much?
Sure. Think of C++ templates like architectural blueprints. Instead of giving the compiler the exact code, you give it a blueprint to generate the code.
Okay.
But with heavy libraries, the compiler has to physically draw and resolve thousands of these complex blueprints for every single combination of data types before it can even start building the program.
So your compile times just absolutely explode.
They do.
Plus, relying on all these external libraries completely wreaks havoc on your infrastructure. Like, the source material mentions they were using CMake CPM downloads.
Yeah.
That means every time their continuous integration system, the automated testing and building pipeline ran, it had to reach out to the internet to download these 7 libraries.
Every single time.
Right. So if a network blips or a package registry goes down, your build just breaks. You are basically importing unreliability.
All for an array size where a raw native loop actually beats the highly optimized external library.
Which is crazy to think about.
It is. This mismatch forced the developer to pivot. They looked at their code and asked, why are we even using extensor?
And the honest answer was just that they needed a few specific functions, right? Like a dot product, array views, and wrappers for fast Fourier transform.
Exactly. Which brings us to the math and how they actually replace that commercial crank.
Right.
The core algorithm for designing these filters relies on Kolmogorov's spectral factorization method, which dates all the way back to 1939.
1939.
Yeah, it is a beautiful piece of classic mathematics.
Yeah.
It uses the Hilbert transform and frequency domain analysis.
But when you strip away the high-level theory and look at the actual code operations required to execute that 1939 math today, it is surprisingly basic.
Very basic.
The computer just needs to calculate cosines, logarithms, exponentials, and it needs to run fast Fourier transforms, specifically real to complex and complex to real transforms.
And again, you only need to run these on tiny arrays.
Exactly. So the developer solution was to drop the heavy framework entirely. They created a custom class called RARR.
Right.
Under the hood, R is essentially just a flat STD vector double. That is a standard built-in C++ container.
Which is so simple.
Here's where it gets really interesting, though, because I have to jump in here and push back a little.
Oh, okay.
This sets off alarm bells for me. Every computer science professor, every senior engineer I've ever spoken to, they drill the exact same rule into your head: do not write your own math library.
Yes, they do.
Ditching battle-tested libraries like Bless or Alapack that have been optimized by PhDs for decades seems like a terrible idea. Aren't you just begging for edge case errors or memory leaks or terrible performance because you aren't a math optimization genius?
It is a totally valid concern, and honestly, in 99% of cases, those professors are absolutely right.
Okay, so why did it work here?
The developers succeeded here because of a concept called hot path optimization. The hot path is the sequence of instructions in your code that gets executed the most frequently. It's the bottleneck.
Got it.
In the original setup, the developer had a tight loop that was running over 20,000 times to design the filter. And inside that loop, they were using those extensor expression templates we talked about earlier.
So what was physically happening inside the computer during those 20,000 loops?
Absolute chaos. For every single one of those 20,000 calls, extensor was triggering 3 separate template instantiations. One to view the data, one to multiply it, and one to sum it.
Oh, wow.
Then it was allocating the result on the heap.
Wait, let's pause on the heap. Why is allocating on the heap a problem for a hot path?
Remember our desk and warehouse analogy?
Yeah.
The stack is your desk. It's incredibly fast but limited in size. The heap is the offsite warehouse. Whenever you allocate memory on the heap, the computer has to ask the operating system to find free space in the warehouse, register it, and give you the address.
And doing that 20,000 times?
In a fraction of a second is brutally slow. And after all that, extensors still had to extract the final scalar value. It was a massive amount of hidden machinery running over and over and over again.
It's the commercial crane trying to make micro adjustments to the TV mount 20,000 times.
Exactly. By stripping all of that away and switching to plain raw for loops in the custom R class, the developer did something very clever. They stepped out of the way and let the C++ compiler do its job.
Compilers are pretty smart these days.
Modern compilers are incredibly smart. When a modern compiler sees a simple, flat loop iterating over a tiny 32-element vector, it performs auto-vectorization.
I've heard that term auto-vectorization, but what is the compiler actually doing to the code?
It's rewriting it to use SIMD instructions. That's single instruction, multiple data.
Okay.
Instead of adding array element 1 to element 1, then element 2 to element 2, sequentially, the hardware processes a whole block of 4 or 8 elements simultaneously in one single clock cycle.
That's amazing.
But a compiler can only do this if the code is simple enough for it to mathematically prove it's safe.
And extensor was too complex.
Way too complex for the compiler to see the optimization. But the plain for loop was perfectly clear. And because they used a standard vector for a small size, they avoided heap allocations entirely.
Yeah.
Everything stayed on the fast stack memory.
The results really do speak for themselves. By getting out of the compiler's way, the hot path became 3 to 5 times faster. That is staggering.
It's a huge win.
But, a 240-line header file sounds great in isolation. The real test is what happens when you roll it out across real-world code bases. Did they actually manage to integrate this without breaking the wider ecosystem?
They absolutely did. Let's look at the actual rollout. The developer applied this minimalist R class to several projects. In the primary one, called multiplierless Crema P, dependencies dropped from 7 down to just 1.
Just one. But actually, I noticed they kept FFTW. If they were so committed to dropping libraries, why keep FFTW? Why not write the fast Fourier transform from scratch, too?
Because that would cross the line from minimalist engineering into pure masochism.
Oh, really?
Oh, yeah. The fast Fourier transform is notoriously complex to write efficiently. FFTW literally stands for Fastest Fourier Transform in the West.
That's a great name.
It is. And it dynamically adapts to your specific hardware. The developer wisely recognized that rewriting an FFT was a bridge too far, even for this project.
That makes a lot of sense. So they kept the one tool that actually did heavy lifting and dumped the rest.
Exactly.
And the build times responded immediately. The CMake configure time was slashed from roughly 91 seconds down to 49 seconds.
Because that CPM download bottleneck we mentioned earlier,
Yeah.
entirely eliminated. And they pushed it to other projects too. The R class was beat directly into another repository called Elalgo CP. For a third project called Core Solver TP, they managed to drop to absolute zero array dependencies.
Zero. That is so clean.
Across the board, first builds were about 55% faster, and incremental builds, the ones developers run dozens of times a day while iterating, those were 73% faster.
So what does this all mean? Well, I want to dig into a specific mathematical win highlighted in the sources, the cosine matrix construction.
Yes.
The spectral factorization step requires building this matrix, which sounds really computationally expensive.
Yeah.
How did the custom loops handle it compared to the giant libraries?
This is a brilliant example of how stripping away abstractions lets you see the actual math better. In the old system, building the cosine matrix involved a double loop that repeatedly called the standard cosine function. It was slow.
Right.
With the new system, they manually vectorized the outer product. But more importantly, they realized they could cache the matrix based on the filter order.
Meaning if you ask for the same filter order twice, it just remembers the answer instead of recalculating the math.
Yes, exactly.
Yeah.
And they went even further. They reduced a multiplier factor from 100 down to 20.
Wait, what does that multiplier actually do? Why was it 100? And how do you just safely chop it down to 20 without ruining the math?
Good question. That multiplier determines the grid density of the frequency response. Imagine trying to draw a smooth curve on a graph. If you plot 100 points, it's very smooth.
Right.
If you plot 5 points, it looks jagged. The original library used 100 as a safe, generic default to guarantee a smooth curve for any possible data.
Ah, a generic default.
Exactly.
Yeah.
But because the developer was now looking closely at their specific small-scale FIR filters, they realized 20 points provided mathematical sufficiency. There was no aliasing, no missed peaks. By dropping that factor to 20, they had 5 times fewer FFT samples to process.
So the combination of shedding the library overhead, caching the matrix, and optimizing that grid density multiplier cut the spectral factorization time by a factor of 5. That is incredible.
It's a beautiful optimization.
But what about my earlier worry about bugs? When you ditch a library tested by thousands of developers, isn't your custom math prone to silent
That's
failures?
the most impressive part.
Yeah.
They use a testing framework called Rapid Check. After all these changes, 100% of the Rapid Check tests still passed, with identical numerical results within machine epsilon.
Machine epsilon. That's essentially the absolute smallest difference between two numbers that a computer's processor can even register, right?
Correct. It means the accuracy didn't drift by even a microscopic fraction. They lost zero precision.
Which brings us to the catch.
Right, the catch.
Because there's always a catch. This wasn't just a magic bullet where they copy pasted a few simple loops and took the rest of the week off, was it?
Not at all. What's fascinating here is we really have to talk about the true cost of minimalism. Minimalism requires mastery.
Yeah.
The developer had to put in serious, painful work to navigate the trade-offs of ditching a massive framework. When you use a big library, it handles all the weird edge cases of the programming language for you.
Right, it protects you.
Yes. When you write it yourself, you suddenly have to fight the C++ compiler barehanded.
Can you give me an example of a fight they actually had to win?
Constructor ambiguities were a huge headache.
Oh boy.
In C++O, a constructor is the code that initializes an object when you create it. They wanted to be able to create an array by giving it a size and a default value, like make an array of size 10 filled with zeros.
Makes sense.
But they also wanted a constructor for a size and a shape for 2D arrays. This C++ compiler looked at both of those options and threw an error saying they were too similar to distinguish.
The compiler got confused.
Totally confused. The developer had to manually remove one of the constructors to resolve the ambiguity and keep the code compiling.
The sources also mentioned they had to wrestle with the semantics of a function called ext where. What is the danger there?
So the where function is used to find the indices of elements that meet a certain condition, like find where all the numbers are greater than 5. The extensor library handles the return format of that function slightly differently than a standard C++ approach. The danger is that if your new custom class behaves even slightly differently than the library it's replacing, the rest of your application will quietly calculate the wrong answers.
Oh, that's terrifying. Silent failures.
Exactly. They had to ensure their new R class perfectly mimicked extensor's specific semantic behavior.
And for that third project you mentioned, Course Solver Solver, ditching the BLS library meant they had to write complex linear algebra operations entirely from scratch.
Yes, they did.
They had to manually implement matrix inversion and something called Cholesky decomposition. What's Cholesky decomposition?
In very simple terms, Cholesky decomposition is like finding the square root of a matrix. It is a highly complex mathematical operation used to solve systems of linear equations.
Sounds difficult.
Writing a Cholesky solver from scratch that doesn't blow up due to numerical instability is incredibly difficult.
Which perfectly illustrates the trade-off. You can only shed a heavy dependency if you have a deeply rigorous understanding of the math you are actually replacing.
Absolutely.
You cannot delete the black box unless you know exactly how to build a smaller, tighter black box yourself.
It is a massive barrier to entry. But, once you cross it, the rewards are exponential. And looking at the source material, this minimalist journey isn't even over.
Oh.
Yeah, they're already planning future, deeper hardware level optimizations for the r.hpp header file.
Right. The sources do highlight a few next steps. The first is span-based views. How does a span-based view improve things?
Currently, when you take a view or a slice of an array, say, looking at just the first 5 elements, there can sometimes be a tiny bit of overhead in managing that subsection.
Okay.
A span-based view is a newer C++ feature that acts as a lightweight pointer. It allows you to reference a contiguous block of memory without copying a single byte of data. It is a true zero-cost abstraction.
Right. Oh, nice. They are also looking at fixed size small buffer optimization, specifically for arrays under 32 elements.
Which perfectly aligns with their core insight. If you know as a hard, unbreakable rule that your data will never exceed 32 elements, you can tell a compiler to allocate exactly that much space on the stack at compile time.
It completely bypasses dynamic memory allocation.
Yes, it's the ultimate optimization for tiny data.
The last future step mentioned is using SSE and AVX intrinsics to optimize the dot product hot paths even further. I know SSE and AVX have to do with the processor, but what does writing intrinsics actually mean for a developer?
We talked earlier about auto-vectorization, where the compiler tries to guess the best way to process multiple pieces of data at once.
Right.
Writing intrinsics means you stop letting the compiler guess. You use special functions provided by the compiler to speak directly in the CPU's native physical hardware dialect.
So you're micromanaging the CPU.
Exactly. You manually dictate exactly which registers to use and how to parallelize the math. It is painstaking, low level work, but it extracts the absolute maximum performance the silicon is capable of delivering.
It really is a triumph of constraints. When you pull all of this together, this entire case study is a massive challenge to the dominant trends in modern software
It
development.
really is.
The default instinct today is always to import a massive generalized library because it feels safer. It feels productive to stand on the shoulders of giants.
If we connect this to the bigger picture, this project proved that sometimes those giants are just weighing you down.
Yeah.
Understanding the physical limits of your hardware cache, trusting the compiler's auto-vectorization, and writing targeted domain-specific code can yield vastly superior results for small-scale problems.
Because context is everything.
Context is everything. What works flawlessly for a massive machine learning pipeline is actively harmful for a 32-tap FIR filter.
I want to reiterate this central triumph for everyone listening, just so the scale of this achievement really sticks with you. 240 lines of code successfully replaced a 7 library dependency stack.
This is amazing.
Just 240 lines of targeted C++ eliminated thousands upon thousands of lines of generalized overhead, slashed build times nearly in half, and sped up the hot path execution by up to 5 times, all while maintaining perfect mathematical precision.
It is the ultimate proof that sometimes the absolute best code you can write is the code you delete.
Totally. To quickly recap our journey in this deep dive, we looked at how developer at Look036 tackled the hidden monster of dependency bloat.
And one.
Yeah. By recognizing that their data structures were incredibly small, just 32 elements, they realized that heavy tools like BLSS cache optimization and lazy evaluation were worse than useless. They were liabilities.
Right.
By shedding the heavy, generalized dependencies of Extensor in favor of simple, native, compiler-friendly loops in a custom R class, they fundamentally changed the performance of their software. And while it required navigating tricky C++ ambiguities and manually rewriting complex math like Koleski decomposition from scratch, the payoff was profound.
It demands a level of craftsmanship that we honestly often lose when we just type install package.
Which leaves us with a final thought to mull over. We've spent this deep dive looking at how a rigorous dependency audit optimized a highly technical piece of software. But what if you apply this exact same dependency audit to your own workflow or even your daily life?
Oh, that is a fascinating parallel.
Right. Think about it. How many mental, organizational, or digital libraries, the complex apps, the convoluted productivity systems, the multi-step daily routines, are you needlessly importing every single day to solve small-scale problems?
It really makes you think.
Where in your life are you currently renting a massive commercial crane just to hang a television when a simple, direct, custom approach is all you really need?
It definitely makes you want to look at your own habits and see what you can delete.
Absolutely. Thank you so much for joining us on this deep dive. Go cancel your metaphorical crane rentals, start trusting the simple loops in your life, and we will see you next time.